teacher, didn't see you there. Welcome to my house. What's that? You like chemistry? Oh, well, I've got some good news for you. In my house, we're all about chemistry. There's chemical reactions happening all around and inside of us all the time. Let's go talk to my friend Charlie the Redwood about it. Come on. Hey, Charlie, you busy? Charlie? Charlie? Turn off the camera, turn off the camera! So, Charlie was in fact dead, but let's find out for how long with the help of my son. Carbon dating. Do your thing, carbon dating. Atomic neutrons bombard nitrogen-14 atoms to transform them into carbon-14 atoms, which are radioactive. Our atmosphere contains about 99% carbon-12, which are pretty stable, about 1% carbon-13, and trace amounts of the famous carbon-14. In living organisms, there is a constant ratio of carbon-12 to carbon-14. Plants and animals are always taking in and expelling carbon dioxide, which in turn gives us the same ratio of carbon-12 to carbon-14 as found in the atmosphere. However, when a living organism dies, the carbon becomes locked in place. No more ins and outs. Carbon-12 is relatively stable, so we can count on it sticking around. Carbon-14, on the other hand, is radioactive and experiences radioactive decay through beta emission and turns back into nitrogen-14. Dating is going to use a mass spectrometer to determine the ratio of carbon-12 to carbon-14. Wow, that was fast. Thank you, carbon dating. Now will you look at that? Here we have the ratio of the carbon-14. But we can use this number to determine how long ago it was that our friend Charlie here passed away. Let's do some calculations. Now, one thing to remember is that radioactive decay is a first-order process. So we can find out how long it's been since Charlie passed away using this equation. The natural log of the ratio of the carbon-14 to carbon-12 when Charlie was alive. And we can put this over the ratio of carbon-14 to carbon-12 when we found him dead. And all of this would be equal to K, meaning the half-life constant, and T, the length of time that he had been dead. Now, how do we find these values? Well, we know that the ratio in the atmosphere is about 1.2 times 10 to the negative 12th. So, this was what was the ratio inside of Charlie when he was still alive. But after he was dead, we measured the ratio of 3.0 times 10 to the negative 13th. Now, one thing that we need to find is, what is the half-life constant? The half-life constant is equal to log of 2 over the half-life. Now, if you'll recall, we mentioned that the half-life of carbon-14 is 5,730 years. When we calculate for this number, we get that the half-life constant is 1.21 times 10 to the negative 4. Now this number can be plugged in for K. And of course, what we still have left to find is the time, meaning how long since Charlie had passed away. All we have left now is just to solve for T. And we can do that simply by dividing. Now what we are dividing here is the half-life constant. And when we do this, we get that T equals 1,457 years. And then this can be simplified to 1.1 times 10 to the 4th years. Wow, that's a long time. I guess we're a little late to the funeral. Sorry, Charlie. But, you know what? He didn't die for nothing. I think he'd make a very nice table, maybe a chair, maybe I'll use him to build a nice little cabin. But I digress. Carbon dating is a useful tool in calculating the time of death for any once living organism within 50,000 years. After that, there isn't really enough carbon-14 to date. On the bright side, we can use other radioactive elements such as potassium, argon, lead, and uranium, which have longer half-lives, to determine the length of much older radioactive decay. Uranium-238 has a half-life of 4.5 billion years. That's a really long time. But it has also allowed us to calculate that the Earth is 4.6 billion years old. This kind of dating requires that we make one important assumption, and that is that the ratio of atoms in the atmosphere has remained constant since the beginning of the radioactive decay process. This is a little rough for archaeologists because industrial activity has pumped large amounts of CO2 into the atmosphere, which has thrown off the ratio of atoms in the atmosphere and affects the rate of decay. Sorry, archaeologists, but thank you all for joining me. You're all invited to Charlie's funeral, and I guess you could say the future of carbon dating is up in the air.